In this video, we're going to start talking about rates of change slightly different than we've been talking about before. We talked about it in reference to linear functions. We talked about average rate of change, which gives us an estimate of the rate of change when we are dealing with functions that are nonlinear. But now we're going to get to what we call the derivative, which will allow us to calculate the rate of change of any function, whether it is linear or nonlinear. And so first, we're going to start talking about instantaneous rate of change. Before we get there, let's review what we know about average rate of change. Remember, if y is a function of t, that means we can write y equals f of t, then the average rate of change of y between t equals a and t equals b is given by the following formula, right? We write this as f of b minus f of a all over b minus a, right? That is our average rate of change, right? And so if we think about a graph, if this is our function y equals f of t, and this is my t-axis, and this is my y-axis here, then if I know that a is here and b is here, then when I calculate that average rate of change for this nonlinear function, this point right here is a f of a, and then I go up to my function here and find the point with that x or t coordinate b f of b. Then the average rate of change is the slope of the line that passes through those points. And remember, we call this line a secant line. So your average rate of change equals the slope of this secant line here, right? And it basically gives, on average, how many units your output or your y is changing for 1 unit changing your input, which here is t, right? That's on average, right? So on average, and it's on average because it's according to this line right here, instead of being according to the actual function here, right? This is how your function is actually changing, but we're using this estimate from this line to help us get that value, right? Remember that your units of your average rate of change is given by your units of y, or your output, divided by your units of t. And one thing that I hadn't talked about before is the fact that notice this numerator is a difference of your y values or your output values, and your denominator is a difference or a subtraction of your input values, right? B minus a. And so what some people call f of b minus f of a all over b minus a, some people call that the difference quotient. In calculus, sometimes we write the difference quotient slightly different, all right? Now, this is a here, and over here to the right of a is b, right? And so let's say that a and b are, I'm going to make up another variable, I'm going to call it h. They are h units apart. So if a is here, and I know that this distance from a to b is h units, then b is the same thing as a plus h, right? If this is h units. And so sometimes you'll see your difference quotient written where b is not written as b, but it's given in terms of a as a plus h, right? And so we can write our difference quotient as f of a plus h minus f of a all over a plus h minus a, because I replaced the b here with a plus h and here with a plus h. Now, when I do that, that denominator becomes very simple. It's just, well, my numerator stays the same, but my denominator, those a's are 0, they cancel, and I have h. This is the difference quotient that you may remember from any algebra-based classes you may have had before. But this is a difference quotient, and this is what we're going to use in order to for us to get instantaneous rate of change. So average rate of change is the slope of your secant line, and it gives you the rate of change of your function on average from A to B. Well, if we want instantaneous rate of change, we want the rate of change of your function at an instant, at a specific point. And the thing that is going to allow us to do this is to let this distance on this interval here to get as close to the point where we want our instantaneous rate of change as possible. So basically, we want this h to go to 0, which is equivalent to saying, okay, well, I'm going to do my average rate of change from A to B, but I'm going to make this distance between A and B smaller, right? For instance, let's say I chose another B, and I calculate the average rate of change from A to B1 here. Well, I'm going to get a different secant line to where it's smaller, well, the distance between them is smaller, and I'm going to get a different secant line. So the slope of that secant line is going to be my average rate of change. Well, if I continuously make the B, or the distance between A and B, so small that I'm basically essentially on top of A, I'm going to eventually get to what we call the instantaneous rate of change, right? And that's the topic of what we're going to do here. The instantaneous rate of change of F at a x value A, or input value A, is also called just the general rate of change here, is defined to be the limit of the average rates of change of F over shorter and shorter intervals around A. And this picture is what I was trying to explain before, right? If we want any instantaneous rate of change at x equals A here, then what we're going to do is we're going to do a bunch of average rates of change, but we're going to let our B get smaller and smaller and smaller to the point where the B essentially lies right on top of A. And when I have all of these B's, I have a bunch of secant lines when I calculate the average rate of change, right? Secant lines. But when I get right on top of A, so that A and B are basically the same, instead of having what we call a secant line, we're going to have a line that just touches the graph at A, but doesn't necessarily intersect it. It's this black line here. I'm not going to draw it because it's going to be messed up. And this is what we call a tangent line. Okay? And so this limit of your average rates of change over shorter and shorter intervals around A, if I go back up to this difference quotient, this different way that I wrote my average rate of change, then in math notation, this is going to be the limit f of b. Instead of writing f of b, I'm going to do that a plus h minus f of a all over that b minus a. And remember, we use a plus h for b, and so we got h there. We're just going to do the limit as h approaches 0. That's equivalent to picking a bunch of b's that are closer and closer and closer and closer and closer and closer to a in order for us to get instantaneous rate of change. Again, the instantaneous rate of change is the slope of this tangent line. And if you want a definition of a tangent line, it's a line that touches a graph at a point but does not cross it, all right? Now, I'm going to be particular here. When we say that a graph has a tangent line at x equals a, we mean that the tangent line touches but does not cross the curve at x equals a, but we don't mean that it can't touch at some other point. It can actually touch at that point, but it's a tangent to the graph at that point. For instance, a tangent line of this function right here, okay, would look like this, right? It's tangent to that graph at this point right here. If we extended it, it definitely would touch at this point, but we're talking about it being a tangent line at this point right here, okay? So these are tangent lines, and we usually don't draw tangent lines to go through the whole graph. We just usually draw them so that we can see where it's tangent at, and it's tangent at that point right there. All right. And so what we're going to do is we're going to start talking about instantaneous rate of change. There are definitely multiple ways that we can calculate these. Before I get to talking about this piece right here, I'm going to introduce some more notation. The derivative of f at a is denoted f with a single quotation mark at a. That's f prime of a. That's how we say that. It is defined as the instantaneous rate of change of your function at a, right? So instantaneous rate of change is the exact same thing as your derivative at a, all right? And it's denoted f prime of a. So instead of using the word find the instantaneous rate of change of your function at x equals a, I can just say find f prime of a, or I can say find a derivative of the function at a. Other ways that I can say that is the slope of the graph of your function at a, and it's also the slope of your tangent line to your function or your curve at a, right? All of these words are synonymous, right? So there's 1, 2, 3, 4, 5 ways that I can say the same thing. I can use this notation to represent instantaneous rate of change. I can say find a derivative at a point That's instantaneous rate of change. I can say, oh, well, find the instantaneous rate of change. I can say find the slope of the graph of the function at a point. That's instantaneous rate of change. And I can say to find the slope of the tangent line. Get used to each of these words here. They all mean the same thing. All right. I'm going to go back a slight, ever so slightly here. There are multiple ways that we can calculate the derivative at a point. When we were doing average rate, well, in this picture here, I wanted the instantaneous rate of change at x equals a, right? And so I had a here, and I chose b to be values on the right side of a, all right? And then I did the limit by doing my average rate of change over a shorter and shorter interval. So I get another b that's on the right of a, get us another b that's on the right of a, get another b that's on the right of a, right? Those are right-sided derivatives, right? Basically, if you have a function and your value a is here, okay, then you're going to choose a b that's to the right on your number line of a and do your f of b minus f of a all over b minus a, all right? You can do a left-sided derivative, right? So if I have my same curve here, and this is my a, and I want to calculate the average, sorry, the instantaneous rate of change at a, then I can actually choose a b that's on the left side of a, but very close to a, right? And then I can do f of b minus f of a all over b minus a, right? Even though b is on the left, this formula still works, right? As long as my numerator is in the same order as my denominator, when I do my derivative, it doesn't matter whether you put a first or b first, all right? And then the last way, you can do the derivative from both sides. And so if I want to find the instantaneous rate of change, or f prime of a, then I can pick a b that's close to a on the left of a, and then I can pick a value that's close to a on the right side of a, right? So I can do f of c minus f of b all over c minus b, right? So there are multiple ways that you can calculate this derivative. The choice is yours. If we don't say calculate a left-handed derivative or left-sided derivative, choose whichever one. If I don't say do it from the right side, choose whichever one that you want to do, and that can give you an approximation for your derivative. All right, let's look at doing this, right? So I have a function f of x equals x squared. We're going to estimate f prime of 1 using smaller and smaller intervals about x equals 1, right? And so I'm going to focus on doing right-sided derivatives here. We'll get to an example where we do it from multiple sides, all right? Remember, you have to use smaller and smaller intervals, right? I'm going to use, and when you think about your intervals, just think about your number line, right? So I have 0, 1, 2, right? I want to find f prime of 1. That's the instantaneous rate of change at x equals 1. Well, the approximation for that is to choose a number that creates a small interval that may include x equals 1. For instance, I'm going to choose a number like 1.1, right? And my approximation means I'm going to use my average rate of change formula and plug in the x values 1 and 1.1 for a and b. All right, what this means I'm going to do is I have to go to my function and plug in 1.1. Now I'm going to write it in here. And you get that into your calculator. Let's see if we get our calculator here. All right, we put that in our calculator, and I'm just going to enter this as I see it on my paper here, right? So I have 1.1 squared minus 1 squared. I put that in parentheses because I'm going to divide that by 1.1 minus 1. I'm going to close that parenthesis and press enter, and I get 2.1. All right, I get 2.1. All right, so let's write this down. Now, that's an approximation, right? So remember, this is a slope of a tangent line, but I'm using this formula to go from 1 to 1.1. So this is a slope of a secant line, right? Now, I want to get as close as possible to 1 so that I know that I get to my tangent line, because that's what we're approximating here, right? So I'm going to do an even smaller interval. I'm going to go from this time 1 I'm gonna pick an interval that's closer, or value that's closer, I'm gonna use 1.001. That's definitely closer to 1 than 1.1. And so that's gonna give me an approximation of my derivative. And so since I'm going from 1 to 1.001, I put that into my average rate of change formula. I go to my calculator. Let's put these values in. So I have 1.001 squared minus 1 squared. And I'm going to divide that by 1.001 minus 1. Press enter. And I'm getting 2.001. You should notice something happening here, right? So we have 1.001 squared minus 1 squared, all over 1.001 minus 1, and we got 2.001, right? This, again, this is a slope of the secant line, and this is what we want, is we want the slope of the tangent line. Now, I could do this again and put some more zeros after the decimal, but before that last one there. And what you're going to notice here is we're going to get closer and closer and closer to 2, right? And so if I want to estimate or find f prime of 1, these are our estimates here, right? Now, in practice, we won't be going over this doing multiple of these. Just starting here will probably get you a close enough estimate, right? But we can tell that there's basically a pattern here, so I'm not going to do any more. But I'm going to say that f prime of 1 pretty much equals 2, all right? F prime of 1 equals 2. And then this, since I use the equal sign here, because my pattern, if I were to do another one, it would probably be 2.000001. I can keep going on and on and on and on, all right? And so it's going to get closer and closer to 2. So this is actually our slope of our tangent line, which is the same thing as our instantaneous rate of change. All right. Now, in practice, if I give you these instructions, all you have to do is just this one right here. All right. Get close enough to 1, or the value that you're trying to estimate the average, the instantaneous rate of change for. All right. I just did both of these so that we can see sort of a pattern. Okay. All right. We said that the derivative is the slope of the graph and the slope of the tangent line. We use the word the derivative at a point. And so we're going to look at this example here where we review how to some information about functional values, as well as some information about derivatives or instantaneous rate of change and how it relates to what things look like graphically. And so in part A, B, and C, we want to determine, well, in all of these, we want to determine whether the quantity is positive, negative, or 0, right? And so in part A, f of 1, whenever we have a function evaluated at a value, and we think about what it looks like on the graph, it's just a y coordinate to that point, which has this x coordinate here, right? So if I want to know if f of 1 is positive, negative, or 0, I go to where x equals 1, find the coordinate, which is this coordinate right here, and think about whether the y value is positive, negative, or 0. This point is below the x-axis, so we know the y value is negative. So we know f of 1 is negative. F of negative 1 is here. The point on my graph is here. That's above the x-axis, so I know that's about 1 point something, which is a positive value. And when I think about f of 3, well, x equals 3 is over here. Looks like we get a value. The point right there, that value is negative 1 point something, or negative 1. That's negative. So remember, when you're determining the sign of a functional value, you just look at the y value, the y coordinate to the ordered pair. Okay? Now when I start using this notation here, what we're going to do is we're going to look at more than just the y coordinate. We're looking at the slope of the graph or the slope of the tangent line. All right? They're the exact same thing here. All right? So if I look at f prime of 1, x equals 1 is here. It's this point right here. I'm going to draw a tangent line just so you can see it, right? So your tangent line is basically a line that touches your graph but doesn't cross your graph at that point, all right? And so it looks like it's just a line that's riding that point of your graph, right? That's your tangent line. Now, the slope of this line is what f prime of 1 equals, right? The slope of this tangent line. All I'm interested right now is whether that will be positive, negative, and zero. So if that tangent line is going down from left to right, that means it's decreasing. That means its slope would be negative. So I have negative. All right, if you didn't want to think about the tangent line, just think about what your curve is doing at that point. Since my function is decreasing at that point, then when something's decreasing, it has a negative slope. All right. F prime of -1. When -1 is at this point, x equals -1 here, I got to try to draw a tangent line, right? A tangent line is a line that just touches but doesn't cross. And if you look on your paper, the tangent line here is going to be completely horizontal. All right, it's just going to touch that because that's at a peak. So it's just going to touch that point. If I drew it any other kind of way, it'll go through the graph at that point. So it has to be a completely horizontal line. And so since that's a horizontal line, all horizontal lines have a slope of 0. And so f prime of -1 equals 0. And then f prime of 3, our function is increasing, or if we drew a tangent line, which is a line that just touches at that point but doesn't cross the curve at that point, it may look something like that. That's going up from left to right, and so f prime would be positive. That's a positive slope. This example here is going to match the points labeled on the graph with the given points. So we have the points A through F. And we have some examples of some slopes there, and we want to match the slopes with the points, right? And so we have some negative slopes, we have a 0 slope, and we have some positive slopes, right? Negative slopes correspond to any points where your graph is decreasing. Or if you drew a tangent line, it would be going down from left to right, right? That doesn't occur with A, because your function is going up at A, your function is going up as it crosses B. But at C, your function is going down, right? If I drew a tangent line, it looks something like that. It touches but doesn't cross at C. At D, your line is going up. E, it's neither going up nor down. It looks like it's horizontal tangent line, right? And then at F, your function is going down, right? And so from at C, you're going down from left to right, and at F, you're going down from left to right. One of them is steeper than the other. The one that's most steep is going to have the higher or the smaller slope. And so F is steep. Okay, C and F are our options here. F is the most steep, so it's going to be most negative, and C is the least steep, so it's going to be less negative, right? 0 is where you have a horizontal tangent line. A, B, and D have positive slopes. A, B, and D. So that doesn't qualify that. And E, your function is neither increasing nor decreasing. It has a horizontal tangent line. So that's the only point where that occurs. So we have that. And then to get the estimates of your slope according to points A, B, and D, we basically have to look at the steepness of the lines, the tangent lines. And so the points with the steepest tangent line. All right, I drew that one a little weird. So the tangent line here, will be something like this. This one will be a little steeper, and this one will be the most steep, right? The tangent line there for point D. So D is the most steep, A is the least steep. That means that B is going to have the medium steepness. All right, so that's just looking and matching slope of tangent lines with values and comparing in that manner. All right, so we've seen a derivative analytically, right? Analytically or algebraically is looking at this to get the derivative. We've seen an example of derivatives graphically or instantaneous rate of change graphically. Now we're going to look at it numerically, right? And numerically is basically using a table, all right? Now, it says if we're given a table of values for a function, we can estimate values of its derivative. To do this, we have to assume that the points in the table are close enough together that the function does not change wildly between them. All right. So with the table of values, I'll be honest with you, average rate of change and instantaneous rate of change is going to be calculated exactly the same way. So it's going to look exactly the same, but we're going to be thinking instantaneous rate of change, right? But what we're going to do here is we're going to look at this example here where we calculate average rate of change and then try to use the average rate of change in order to get the instantaneous rate of change. And so we have the position S a car at time t given in this table here, right? So my input variable is t, which is given in seconds, and our output variable is s, which is given in feet. The rate of change of an object that's traveling is always the position divided by the time. All right. Some people might remember distance equals rate times time. And so if you divide t on both sides, distance over time equals rate. And this to kind of give you the velocity or the speed and all that stuff like that, right? So if we want to calculate average velocity, we basically calculate the average rate of change over this interval here, and we're going to do it from 0 to 0.2. And so that's going to be S of 0.2 minus F of 0 all over 0.2 minus 0. And what's nice about tables is we always get the functional value without having to do any work. And so that equals, I've done that myself already. That equals 2.5. And it's going to be the units of your numerator, which your S is in feet, divided by units of your denominator, which is in seconds, right? So that's your average velocity, right? That's like the average rate of change of position over time, all right? Or with respect to time. We're gonna do the same thing from 0.2 to 0.4. And from our table here, 0.4, our output is 1.8, 0.2, our output is 0.5. So we'll have a 1.8 minus 0.5 all over 0.4 minus 0.2. And if I did that right, I'll get 6.5. My units again are feet per second, right? Now, I've calculated the average velocity. It's over a small interval that has to do with 0.2, all right? Here in part B, I did the same thing, but I did it with the interval from 0.2 to 0.4, right? Another way that I can ask this is I can ask, find the instantaneous velocity at t equals 0.2, right? And I'll be honest with you, all right, because we're given a table of values, right? Because we're given a table of values, this answer right here is one of the approximations or one of the solutions to finding that right there, all right? That is one, because we can't do smaller and smaller intervals. We only have the intervals that are given to us in the table, right? So I don't want you to get confused here. If I change that word from average to instantaneous, you would do the exact same thing. Now, when I told you about the derivative, if you look at 0 to 0.2, all right, this is actually, if you think about your number line, 0 is to the left of 0.2. So this would be an estimate if you were using a left-sided derivative. Because if I'm focusing on t equals 0.2 on my number line, 0 is to the left of 0.2. And so if I use this as a proxy for my instantaneous rate of change, what I'm calculating here is a left-sided derivative. In part B, we use the value 0.2 to 0.4. And so if I were focusing in once again on t equals 0.2, since 0.4 is to the right of 0.2, this would be considered a right-sided derivative. And so I could use this as an answer to finding the instantaneous rate of change also, right? But this is just using a right-sided derivative. So I can use a left-sided derivative, a right-sided derivative. But what we generally like to do when we're given a table of values is to use both the left-sided derivative and the right-sided derivative to give a better estimate, right? So when we did the left-sided derivative, we got 2.5 feet per second. And when we did the right-sided derivative, we got 6.5 feet per second. And so a better estimate of the instantaneous rate of change is to use these average rates of change, which we got from the left and right-sided derivative, but to take the average of them, right? And so we're going to say that S prime, because my function is S instead of F, and we can write it that way. 0.2. This represents instantaneous rate of change. The better estimate would be to do the left-sided derivative plus the right-sided derivative and divide that by 2. And we're going to get 4.5 feet per second. All right. This is equivalent, and I'll let you check this on your own, to doing the derivative from both sides. All right, that's always going to be the case. All right, and so this concludes this video here. I'll see you next time.